Hello, this is the second of a series of videos on how to model a reinforced concrete beam in Abaqus. One very important thing I failed to mention in the first video is that you must save your module continuously in case there's a power shortage or you run out of battery or you click on X and close the program. So as in any other document, just go File, Save. Okay, so let's continue. We're gonna create partitions for loadings, restraints, and to monitor specific model elements to get displacement, strains, and forces. So go to the mesh module, and then we need to partition some of the faces for this particular model. So from the icons on the left, click on partition face sketch. It says dependent part instances cannot be edited or assigned mesh attributes. So it says we need to make the operation on the related part, the part itself, which is this part. So now we can operate on it. So click on partition face sketch. And now it says sketch the faces to partition. Select the faces to partition. We're gonna create partition to apply the displacement. So we select the top partition, the top face. Now it says click done, and then it's asking us for an edge that will appear vertical and on the right. So that will be this one. And we're ready to sketch the partition for the displacement. The load points are 22 inches apart from the center line, which will be this line here. So we only need to create a partition 11 inches or units from this left edge, and we'll apply the displacement here in the negative y direction. There are many ways of doing that. The easiest one is to click on use the offset command. So click on offset curves, and it's asking us to select the entities to offset. So it's this line where we want to offset ODH. Click done, and the distance is 11 units or 11 inches. Is the offset shown on the correct side? Yes. If it doesn't, you need to flip it because it may be on this side that you can't see. So click OK, click done, click done. Now we have our first partition for our displacement. So now it's asking us again to select the faces to partition. We're gonna rotate it a little bit, the beam, and create a partition for the boundary conditions. So press escape to exit the rotation command. Sketch the select the face to partition, click done, and then select an edge or axis that will appear vertical, and on the right that will be this one. And we are ready to sketch. So now we need a boundary condition here, here that will be 2 inches away from this left edge. So we again use the offset command. Select the entities to offset, that would be this line, click done, and now we're only going 2 inches. Is the offset shown on the correct side? No. We flip it, and now it's shown on the correct side. Click OK, click done, click done again, and now we have our partition for the boundary conditions. Let's go isometric. So this also comes from this setup. The boundary condition, which is the support, is 2 inches from the edge, and then the load points are 22 inches apart. So we went 11 inches from the center line this way, and that's gonna put the first load point or the displacement point at 11 inches from the center line. Let's go back to Abaqus, click done. Okay, so now we're ready to create boundary conditions and assign loadings or displacement to the partitions we just created. So we change the module to load, and we're gonna create a boundary condition. Name the boundary condition. The first is gonna be displacement, and step 1, this is the step we created, and the procedure was defined when we created the step. It's mechanical, and then the type is gonna be displacement rotation. We continue. Select the regions from for the boundary condition. The region will be this line here, which is the partition we created. Click done, and it says displacement. We want to go in the y direction, which is this is x, y, z, and then these are rotations. We don't worry about rotations for now. We're gonna go -3 inches. Click OK, and you can see those arrows signify the direction of the displacement. Now once again, click on create boundary condition, and this thing is still gonna be displacement or rotation. Let's rotate the beam a little bit so we can see the bottom partition we created for the support. Press escape to exit the rotation command, and then name the boundary condition support, and then click continue. Select the regions from the boundary condition. That will be this line. Click done, and then click the displacement on the y direction 0. So we want it to go up and down, not into or out of the page. That would be the z-axis. It doesn't hurt to constrain it in the x and z direction, but it's not necessary. We may need to go back and constrain them in case then when we're visualizing it, the displacement, if it deflects as it's supposed to, and then it also shifts, is because the support conditions weren't applied or defined properly. For now, let's just go with y, 0 movement in the y direction, and click OK. And you can see those symbols signify the constraint created on that boundary condition. So now let's change the module to mesh, and we're gonna measure parts, which is the beam and the steel reinforcement, but we need to seed the parts with the size first, and the seed size is important because this affects the analysis time. An inch will be adequate for this type of analysis, but we're gonna go a lot smaller than that. With 1 inch it will take about 10 minutes to run this analysis, or less than 10 minutes. With ½ inch it'll take like 25 minutes, but we're gonna go with a 1/4 inch to get more accurate crack patterns, which will take about 35 to 40 minutes for this quarter of a beam. That's why it's important to module just any module. Just if there's symmetry, just model a quarter of it, and then apply boundary conditions to create symmetry boundary conditions, and then from the results extrapolate your numbers as needed. So go to seed, select the beam first, seed part, and then the approximate global size is going to be 0.25 units or 0.25 inches, and we don't worry about this. We'll leave them as is, the defaults. Click apply, click OK, and now highlight the beam, go to seed part, The approximate global size is the same size, 0.25. And this again is the default. Click apply, click OK. Before we mesh the parts itself, let's do a quick check on the mesh controls. So go to mesh and then controls, and it says select the regions to be assigned a mesh controls. Let's select the rebar first. Click done. Okay, let's try it again. Controls, select the regions to be assigned mesh controls. Let's try the beam. Mesh controls. Okay, wait, no, not that. Mesh controls. This, we want it to be the element shape hexagonal and the structure technique. So for this part, it's okay. Let's go back to the rebar. Element type. Select the regions to be assigned an element type. Select the rebar. Click done. And I think we need to change this for only for the rebar itself, because it's a wire and it's a truss. So we need to change it to truss. Otherwise, we'll get an error that section the property definitions are missing or incorrect for some sections. So it needs to be a truss. Click OK. Click done. And then let's try to check it again. Controls. No, I guess it just did it for the beam. But if the beam has that structure technique, then the rebar has to have that structure technique. So now let's go to mesh. Part. Okay, to mesh the part, click yes. And it's gonna change to aqua, which means that it's already been meshed. Let's go to the beam. Mesh. Part. Okay, to mesh the part, yes. And it's all meshed. Now, before we move on to the next module, or the next step, which is creating sets to monitor forces, displacements, and strains, we're gonna create symmetry boundary conditions. So go to property. Step. Load. Oops, after 20 trials. And then click on create boundary conditions. And let's call this one symmetry. And it's gonna be symmetry and asymmetry and caster. Click continue. Select the regions for the boundary conditions. We're gonna rotate it a little bit. It's hard to rotate. Press escape to exit the rotation command. This face is going, it's perpendicular to the z-axis, so that's the face we choose. Click done, and then we're gonna go Z symmetry and click OK. And then let's create a second boundary condition. It's also symmetry, and now we're gonna call this X symmetry. Click continue. Rotate it again. We don't need to rotate. I'll change it to isometric so we can see this front face is the face. It will be considered a slice on the center line of the beam, and we want Abaqus to think that there's another piece of beam or a mirror image of it. I'm saying think because we know that there's nothing there and nothing's gonna be integrated, but we need to specify the boundary condition so that we can double the force this way, and then it's gonna be quadruple if we take into account the other symmetry that's on this side. So click done, and in this case it's gonna be the X symmetry. Click OK, and that's all we need. So now let's go back and create our sets. So expand the assembly menu from the model tree and double click on sets to create our sets. We need to name the set. This one we're gonna call it displacement monitor, and the type is gonna be node, and click continue. Let's get close to the center line. I'm gonna zoom into it. Press escape to exit the offset command. Let me rotate it a little bit so it's easier for me to see. It's not easier. Escape. YC, zoom in. Okay. Nodes. Can't select it. Done. Nope. Okay, there. Let's try this one. It's only, yeah, it's pretty significant, a quarter inch of a difference. This is a quarter inch. I just can't. Okay, let's try this one. Works the same way. Click done. And that's our first set. The deflection on our real beam was measured at midspan with a height gauge right around here, so I don't think it matters if we go into the page a little bit, because the displacement is going to be taken from this horizontal datum down this way, so we're okay. Now the next set is going to be created to measure the reactions on the beam at the load point caused by the prescribed displacement, and one set will be used to represent quarter of load points, so the resultant force will need to be quadrupled since we'll be only monitoring a quarter of the force and we only modeling a quarter of the beam. So we double click on sets. Let's name the set load bar. It's gonna be a geometry. Click continue. Let's show the full isometric view. Let's select the load bar and click done. And the second set has been created. Now the last set is a set that will monitor the compression strain on the concrete itself, and that will be the last set for this demonstration. In future videos I'll attempt to add different external reinforcement polymer plates, such as carbon fiber or natural fiber polymer plates, just like as it's shown here. This is actually an FRP plate, or a natural fiber reinforced plate, that increases the load bearing capacity of the beam itself, or in case the beams crack, it helps restore its original strength or capacity, or increase the carrying capacity too. But right now we're just gonna monitor the strain on the compression phase of the concrete itself. So let's double click on sets and name this compression strain. It's gonna be a node. Click continue. The strain was measured at different locations on the beam. The compression phase, it was 1 inch on the center line from the top of the beam, and then there was one on the opposite side of the beam on the back, and then there was one on the bottom, one at 3/4 of the distance of the beam, and one at 1/4 of the distance of the beam from the supports. For now we're gonna monitor only one, but you can have as many as you want depending on what the purpose of your analysis is. So now I need to rotate the beam a little bit. Okay, now escape to exit the rotation command. I'm gonna zoom in a little bit here. Each block is 1/4 of an inch. So our beam, the strain gauge on our actual beam was 1 inch from the top. So that will be 1, 2, 3, 4 squares. And then it was like 1 inch or 3/4 of an inch wide. So if I select this, okay, now I'm gonna cancel it. Press escape to cancel it. I'm gonna have to create it again because I picked the wrong parameter. Instead of node, it had to be geometry. So let's go back, name it compression strain. It's gonna be geometry element. Continue. 1, 2, 3, 4, and then we select this element. Press shift and this element. Click done. And now we have all 3 sets. So now we change this module to the step module. And we need to create output requests from our module, which is data could be energy, displacements, forces, strains, stresses, and so on, depending on what you're modeling. But the analysis could give you huge amounts of data. But we can control which output to request so that only data required to interpret the results of the simulation is produced. So we are only interested in the RDB and the .dat output types of the 4 available in Abaqus for this analysis. So the output database, or the .rdb file, is for visualizing purposes, and it's also used for by Abaqus for post-processing. And the other output types are printed tables of results. They're written to some .dat file, and we'll use these results from tables and import them to Excel to plot the results and compare them to our actual experimental results. So when we created step 1, Abaqus generated default output request for the step. So as a quick check, go to steps, click on initial, field output request, double click on field F output 1, and you can see what Abaqus deems necessary for our analysis. Click cancel. We may not need all this, but we'll leave them like that for now. I added the failure fracture damage. Click OK. But we need to define our own field output requests so that we get information from the sets we just created. So the field output request is for the whole module, and they get recorded at lower frequencies to the output database, but we want to use the history output request because this option records the variables at high frequencies for a smaller portion of the model, such that displacement we want to monitor. That's really important for a load and displacement curve, or the forces on an element. So the steps will be the same for the three items we're interested in, which are forces, strains, and displacements. So let's create step 1. Let's go to step 1, history output request. This is the default history output request created. Let's double click on history output request to create our first history output request. So name this history output displacement. On step 1, click continue. It says, what do you want for the displacement? We want the domain to be the whole module. We want it every n increments. We're gonna get quite a bit of data here, but let's leave it as n equals, let's change it to 100. And then for the output variables, we're just interested on the displacement. Okay, we need to change this domain because I'm not getting the options I want. It can't be the whole module. It has to be the set we created, and the set is the displacement monitor. And now we have more options here. We want U, translations, and rotations, and we only want the U2 translation, which is the translation in the y-axis. And you can see the output variable is only U2, which is what we want. And click OK. Let's create another history output request. We'll call this one strain. Step 1, click continue. And again, we change it to a set, and the set is the compression strain. Let's change this to 100. And if we don't see a curve that kind of resembles the load versus displacement curve, the typical curve for concrete, we'll go back and decrease the n. But for now, let's leave it at that. Otherwise, we'll get like a large amounts of data. And then for the output variable, we want strains. E, total strain components, and we want E11 only. You can get several ones, but for our case, we use unidirectional strain gauges, and then we're going in this direction, which is the y direction. So that's why we want the principal strain, which is 1, in the one direction, which is x, and that's what we want for now. If you had a compression analysis, say of concrete cylinder being compressed, then you will need to go in all three directions, 1, 2, and 3, and so on and so forth. But in our case, we're the only data we have to compare. This particular analysis is the unidirectional strain gauge data we got from the lab, and that's what we're gonna use. Click OK. And now let's create our last history upper request and name this one force. Click continue. Set load bar n equals 100, and then we want forces, reactions, reaction forces and moments. We want the reaction force on the y direction, which is reacting to the applied displacement here on this area. Click OK. So we are ready to run the analysis. We constrained it, created, assigned materials, properties, sections. We set up field and history upper requests. So let's change the module to job. And then click on job manager. Create a job. Let's name the job job 1. If we have problems, we'll fix them right now, because I've been running some analysis and I don't change the job names. It's just job 1 time and time again. I extract my data and put it whatever I wanted, but if we do, we'll fix it. It's not difficult to fix. Click continue. Full analysis, run in the background, submit immediately, and then you don't have to worry about this. In our case, precision, memory, how the computer runs, and so on and so forth. Click OK. You have your job 1 created. Before we submit it, we have to check it. So let's check the data. Yeah, this is what I was talking about. It's alright. Click OK, and then monitor. This will tell us if there's warnings of errors, the job monitor. And we didn't even get that far because we have an error. It says detected log file job1.lck. Okay, let's try to fix that. So we go to C, temp, and see if we can find the file Abacus is complaining about. Delete. Yes. Okay, close. Close this. Check the data again. Click OK. Monitor. Check the warning stuff first to see if we have any warnings. Even sometimes if we have warnings, the model may still run, but we'll see. Okay, this is because I picked damage separation, and so there's not going to be output for that, but we don't have to worry about it. But XFEM is like some special type of crack detection surface for Abacus. We don't have to worry about that. So if the check completes and these are the only warnings we get, so we should be okay. And then you can see here that it's completed. So we closed, we don't have to close the job monitor, we actually want it open. So we go and submit our job, and it's gonna analyze it. And if we encounter warnings or errors as the analysis runs, or if the analysis aborts, then we'll have to go back and refine our module. But for now, I'm gonna submit the job. Click OK, and then open the job monitor, and it's gonna start iterating and integrating and doing the background stuff to get results. So I'm gonna stop here because it's gonna take about, I don't know, maybe 40 to 1 hour, and in the next video we'll talk about visualizing the results and exporting data to compare to actual experimental results. Oh, don't forget to save your file.